Hi, and welcome to this online video lecture on the laws of thermodynamics. Unit number 8 in this course is on thermochemistry, which is all about how energy is changed and modified and transferred from place to substance when chemical reactions occur. In order to really understand thermochemistry and what's going on there, we need to first examine what are called the laws of thermodynamics. Now, there are several laws of thermodynamics, and they're basically kind of like mathematical rules for what happens when energy moves from place to place or different kinds of changes happen. For this course, we're really going to only focus on the first and second law, even though there are several, there are more. And by the end of this lecture, you should be able to take everyday kind of common situations and analyze them in terms of either the first or second law and explain what's going on there in terms of energy. So let's get started. We're going to do the first law. It's called the first law of thermodynamics. So I'm not going to write of thermodynamics every time because the title says laws of thermodynamics. So probably the easiest way for me to first start explaining what this law is about is by writing kind of like almost like an equation. And that is energy in equals energy change plus energy out. And so basically what the first law says is that when you have a system, which is just basically like saying some part of the universe that you're looking at, when you have a system and there's an energy change in that system, the energy in is going to equal the energy change plus any of the energy that leaves the system. So another way of looking at that, you can kind of move the things around. Another way of thinking about it is that the energy change equals the energy in minus the energy out. So you can kind of think of it either way. Now, there is a reason why I wrote it this first way, but before we go a little bit further, let's just talk about the fact that in chemistry, most of the energy that we're going to be talking about is heat energy. And so when you measure the temperature of something, what you're actually doing is you're measuring the amount of heat energy that is inside of, oh wow, I messed that up, inside of that matter. So oftentimes when we are talking in this unit about energy, we're oftentimes going to be talking about heat energy. So let's just take kind of a theoretical situation, an everyday kind of a situation, and we'll look at it in terms of the first law. Let's say we have a little hot plate, and on the hot plate we have a burner, and inside of the burner we have some water. And right now the water is 22 degrees Celsius, which is basically room temperature. Now, if we turn our hot plate on, I think most of you know that energy is going to move from the hot plate into the water that's in the beaker. So that's our energy in. Oops. So as the water sits in the hot plate, energy is going to move in to that water from the hot plate. But at the same time, water is going to be moving, or energy is going to be moving out of the water into the beaker. It's going to be moving out of the water and into the air. And some of it might actually move back into different parts of the hot plate depending on how hot or cool the hot plate is all over. So now here's where the first law comes in. If we could measure all of the energy that went in to the beaker, and then let's say that the water temperature increased from 22 degrees Celsius to 80 degrees Celsius, then we could measure the energy change that accounts for the water, that much water increasing that much temperature. And let's say we could measure every single bit of energy that came out. This is where the first law comes into play. All of the energy in has to be equal to the energy change in the water that caused the temperature to rise, plus any of the energy that left the water. So basically, what this is saying is that you can account for all of the energy that's going into the system. It either causes the water's energy amount to go up, or it might be lost outside of the system to some other matter, some surrounding matter somewhere. But if you add those two things together, the energy change in the system and the energy that was lost outside of the system, then it should equal the energy that you put into the system. That's what the first law says. And basically, one of the main ideas here that the first law is trying to communicate is called the conservation of energy. And that basically just says that energy can't be created or destroyed. And the destroyed really is probably the more important part of that. Because at first glance, what happens is if you were to just look at the energy you put in to the water, and then you just looked at the energy change, you would say that some of the energy that you put into the water disappeared. It got destroyed. But that's not true. Some of the energy that you put into the water actually came out of the water. It got transferred to the surrounding air or the beaker or somewhere where you weren't looking. It did not get destroyed. So you just have to kind of keep that in mind. All of the energy that goes into something is either going to remain in the new system or it's going to maybe leak out into some of the surrounding matter around the system. It's never just destroyed. It never just disappears. So another way of kind of thinking about that is if there is no energy change. So let's say we have a new beaker of water. And again, this beaker of water is at room temperature 22 degrees Celsius. Let's say that we, again, heat the water up. We put it on a hot plate and we heat the water up. And then we take the water and we just set it on a table. So now we have some hot water and it's just sitting on a table. Well, what's going to happen to that water? We took it, we heated it up to about 80 degrees, then we set it on a table. I think everyone in here knows that what's going to happen is the temperature is slowly going to decrease until the water again hits room temperature, 22 degrees Celsius. And so if you let that happen, if the water starts at room temperature, you heat it, you take it off and you set it down, and you let it cool, and it gets back down to room temperature, that means that the energy change inside of the water is zero. So what does that mean about the amount of energy that went into the water from the hot plate that caused it to heat up from 22 degrees to 80 degrees Celsius, and the amount of energy that left the water, and most of it probably went into the air, but some of it might have gone into the table or into the beaker, that caused the water to drop back down to 22 degrees Celsius? Well, if we look at the first law, scroll back up here. The first law says that energy in equals the energy change plus the energy out. Well, the energy change in our example is 0 because the beaker started at 22 degrees Celsius and it ended at 22 degrees Celsius. So what does that mean about the energy in, which we're representing with the red energy arrows here, and the energy out, which we're representing with the yellow arrows? Well, if you think about the first law, energy in equals change in energy plus energy out. Well, our change in energy is 0. So basically it just cancels out. So what does that mean? It means that the energy in has to equal the energy out. So however much energy we put into the water to raise it up to 80 degrees Celsius, the exact same amount of energy has to come out of the water and go into the atmosphere or the beaker or the table when the water drops back down to 22 degrees Celsius. The energy in has to equal the energy out. And the reason for that is the first law. I made an I there. The first, oh my gosh. Let's just try that again. The first law. So a lot of children will just say that the energy just disappeared or went away or maybe was destroyed. But we know because of the first law, energy can't be destroyed, and the formula illustrates that. All of the energy that goes into a system has to equal all the energy that comes out of the system if the system's internal energy doesn't change. So that's the first law. It's kind of a simplified version of it, but that's basically what you've got here. An energy change of a system has to equal the energy in minus the energy out, or another way to think of it is the energy in has to equal the energy change plus the energy out. That you can't just have energy just kind of disappearing somewhere. It's always going to be accounted for somewhere. So that's the first law. Now let's look at the second law. So this is the second law of thermodynamics. The second law has to do with a concept in science that's called entropy. And oftentimes you'll hear entropy as a concept described as disorder. Whoops. Disorder. What this kind of translates to in terms of energy is the concentration of the energy or the usefulness of the energy. So when matter has low entropy, then that means that the energy concentration is high. They're opposites. If you don't like to think in terms of concentration, you can think of usefulness. And if the entropy is high, the disorder, the randomness of the matter is high, then usually that means that the energy concentration is low. Low. And again, if you don't like concentration, you can think of it in terms of usefulness. And so what the second law says is that whenever you have any kind of a change, the total entropy of whatever you're examining has to go up. So all changes increase entropy. Now that means the total. Sometimes if you're looking at just a part of something, it looks like the entropy is going down. That can happen. But if you look overall, then the entropy has to increase. Another way to think of this is that energy always goes from high concentration to low concentration. And again, if concentration is confusing to you, you can replace it with usefulness. Energy goes from high usefulness to low usefulness. And this is what's called the second law. So let's apply this to an example or two, and we can see if we can start to figure this out a little bit. Imagine if you took like a piece of metal, say a little cube of aluminum or lead or something like that, and you heated that up with a blowtorch. Not high enough for it to be melting, but high enough for it to get really pretty hot. So you have this cube and you've heated it up, and now it's gotten really, really very hot. Now let's say we take that little cube of metal and we place it into a beaker of water. At this point, the cube inside of the water represents an area of high concentration of energy. So the cube it's a source of very, very concentrated energy. And so what's going to happen is the energy is going to go out of the cube and into the water. And so as this happens, what you're going to see is you're going to see the temperature of the cube drop and the temperature of the water rise. And that's going to continue to happen until the cube and the water are relatively the same temperature. And then at that point, the energy going into and out of the cube and into and out of the water is going to be relatively the same because the temperatures are the same. So let's examine how this actually illustrates the second law. The second law says that we have to increase the overall entropy. Energy, in other words, energy has to go from a high concentration to a low concentration. So when we put the cube in, at that point, that's a source of very concentrated, a high concentration source of energy. There's a lot of energy in that little bit of matter. Whereas the water represents a low concentration of energy. And that's why the heat moves from the cube out into the water. And then eventually what happens is the heat will continue to move from that high to low area until the water and the cube have the same concentration of energy. And then at that point, the energy transfer is the same. The energy that's going out of the cube into the water and out of the water into the cube is the same, and so they'll just remain at the same temperature at that point. So this is an illustration of the second law because it's an example of a system where energy is moving from a high concentration, which was the cube, to a low concentration, which was the water. If we look at the overall entropy of this system, the concentration of the energy in the cube has decreased. Now, the concentration of the energy in the water might have increased a little bit, but the overall change is going to result in a lower concentration overall than what we had before. And there's one more thing that we haven't talked about yet, and that is while the heat energy is going from the cube to the water, we might be losing some heat energy to the beaker. We might be losing some heat energy to the air. And so what happens is a lot of that energy that was in the cube is lost, not destroyed, but lost outside of the system. And so when we're done, we have higher entropy, the energy is less concentrated overall, and some of the energy's actually left the system due to the nature of the water touching the air and the beaker and things like that. So that's the second law. Changes increase entropy, and the energy is going to move from a high concentration to a low concentration always. Now, before we end this lecture, I know it's getting long, but I do want to talk about one specific instance or an example of instances where the entropy will actually decrease in part of the system. So if you think about like a human, here's a person. I'll make him a stick person. Okay, so here's a person, and this person's going to eat an apple. There's our apple. Now, when the person eats the apple, an interesting thing happens. The energy that's in the apple is already pretty high, but the person's body takes that energy and it converts it into ATP, which you should remember from biology class, which is usable energy for cells. So it's taking energy that's already pretty highly concentrated, but it's concentrating it even more. It's making it even more useful. And so at first glance, it looks like the human body is decreasing entropy. But what you have to keep in mind is along with a little bit of the apple's energy being turned into ATP, just a little bit of it in your cells, a great amount of that energy is being given off from the cells of the human as heat and not getting turned into ATP, like a bunch of it. So that energy that's given off as heat is a much lower concentration, much less useful than the energy that was turned into ATP. So sometimes in a system like the human body, you can actually lower entropy a little bit in one small instance, but the payoff is that there are going to be other instances where it's greatly increasing the entropy and creating a whole lot of not very useful energy. You can't really use this energy. It's lost to the human body. It's can't be used to do any work or anything like that. So sometimes you have to be careful. There are sometimes instances where you can take energy and actually make it, some of it, a little bit of it, more concentrated, but the vast majority of it is going to become much less concentrated. So a little bit of it becomes more concentrated, and much more of the energy will become less concentrated. And that's about it for our Laws of Thermodynamics video lecture. Make sure that you understand these two laws, that you can think about things that happen in your life and apply these two laws to them to try to explain what's going on. Things like, a melting ice cube, or a car burning gasoline to drive down the road or light its lights. And if you feel comfortable with these two laws and you can explain things, you're probably in pretty good shape. So that's going to be it for now. As always, if you have any questions, please feel free to ask in class. And thanks for watching.